recording. Okay, great. So gravity worksheet, that's great because that is also the writing prompt, right?
Yes.
Okay, good. Okay, so it's open and you can go if you want by one by one, and then I can give you feedback.
Okay. Let me open it also. So for the first one, wouldn't the Earth exert a greater gravitational force than the Moon because it has a greater mass than the Moon?
Okay, so I'm not going to give you the correct answer, but you read whatever student Y and Z say, because one is correct and one is not correct. So let's see which one makes more sense.
Oh, but for number one?
I know, but what they're talking about is related to the number one.
Okay. Okay, so okay, so I think student Z is correct because the Moon and the Earth do not exert the same gravitational force on each other, I think. Is that
And
right?
why do you think that?
Because of Newton's law of gravitation.
Okay, so which tells you what? It says even here, okay? So here is like, for example, read this and then like carefully read and tell me what does it mean. Basically, especially this, right? Between any two bodies. So to define the gravitational force, right? You have to have two objects. You cannot just say like, you know, Earth's gravitational force. It has to be like between you and the Earth, right? The force is always between two objects.
Yes.
Okay, so then the gravitational force between the Earth and the Moon, like looking at this equation, what does it depend on? This G, whatever, you can ignore it. That's just the constant. But what's the big M and what's the little m?
The masses of the two objects.
Yes. So big M, let's say, would be like the Earth because it's bigger, and then little m is the mass of Moon, and then D would be the distance from one center to another center, right? So if you're talking about two big objects, two massive objects where you can have like measurable gravity between them, that force of gravity between them depends on both of their masses, and they both feel the same force. Simply that's like, you know, what the gravity is.
So they feel the same force, but the Earth exerts a greater gravitational force?
No, the force that they feel is the one that it's exerted on them, right?
Yeah.
So the force comes because both of them have masses, and the objects, like, you know, just think about yourself. You jump on the Earth pulls you down, right?
Yeah.
And so the Moon and the Earth are pulling kind of with the gravitational force towards each other. And so they pull with the same force because the amount of that force simply depends on both of their masses and their distance, nothing else. But I absolutely know what is confusing you, okay? Because I also teach physics as well. And this is like, even for physics, the problem. So what I think you're confusing in your head is basically like the force and the response to that force, or the acceleration. So the force that both of them feel is the same because, like, you know, as I said, because of the definition depends on both of them, right? If they were bigger, there is more force. If they're smaller, there is less force. If they're closer, there is more force, and so on. But the force does not have the same effect on them, right? Does not affect the Earth the same way as it affects the Moon the same way, right? And it does not affect them the same way because they have different masses. And so that's really hard to understand. Like, even in physics, really students get confused, but there is this acceleration, right, that basically is like how the objects respond to the force. So you apply, here is the force, you apply the force to an object. How the object will respond to the force depends on their mass. And so, like, you know, if the Moon and the Earth feel the same force, but Earth has way more mass, 4 times more mass, right? So it's going to be affected 4 times less by that force. The force will affect the Moon more because it's, like, you know, tinier.
Okay.
Does that make sense?
Yes.
It really is like the common sense. It's just like absorbing kind of this language of physics, because you can think, you take somebody big, like a sumo wrestler, right? I don't even know how heavy are they, 500 pounds or something. And then you take something small, like my son has like 40 pounds, okay? And then you push them with the same force. They're not going to respond, right, the same way. The big one will basically do nothing, yes, but the little one might even fall down or roll, depending like how hard you push them.
Yes.
So in the lecture slides, for example, I think I asked you also about the sun and the earth. The same thing now. You can apply the same formula to the sun and the earth. This would be the mass of the sun. Let's say this would be the mass of the earth. Both of them are going to feel exactly the same gravitational force because of each other, right? But the sun is like so much more massive than the earth, right?
Right.
So that force basically will do nothing to the sun. And yet that force makes the earth basically go around the sun.
Which is why the earth orbits around the sun, because
exactly
it affects, okay, it makes sense.
Does that make sense? So the force is the same, but depending on your mass, like that will determine how you respond to the mass. And I think that's like kind of what you need to think to help yourself kind of I don't know, overcome the misconceptions, I guess.
Yeah.
Okay, good. So then the answer for the number one would be exactly what student Y tells you, right? He's completely correct. Student Y states the law of the gravity correctly.
Okay. Got it.
Okay, how about number three?
How would the force between the moon and the earth change if the mass of the moon only were somehow made 3 times greater? Would it even orbit the earth anymore?
Don't even think about that, okay? So this is all like hypothetical, right? So they're just like asking you to think about this expression about the force, right? What would happen to that force if somehow you make the mass of the moon like 3 times greater?
Okay, so the moon would have a greater gravitational pull.
Not the moon, but the force of gravity between the moon and the earth. What would happen to that?
It would increase, correct?
Correct. How many times?
3 times.
Yes, because if you think about this formula, right, let's say this is the mass of the earth. Now you add instead of mass of the moon, 3 times the mass of the moon. That means you're going to get like 3 times more force.
Right.
So if somehow you could make the moon more massive, then the force would be greater. And so that's the rule, right? The more mass is there in the like whatever objects, planets, stars, whatever, the more force of gravity is there.
Makes sense.
Good.
Okay. And so for number 4, force, the distance between them was somehow made 3 times larger. So 3 times larger. So distance squared. Would we have to square the number?
Yes, exactly. Very good. So if the distance is larger, the first answer is is the force weaker or stronger?
It would be weaker.
Very good, because the farther they are from each other, the less force they will feel. Very good. And then you're paying attention that you cannot just say 3 times, but you actually have to square the distance, right? Yeah. So it's more sensitive to the distance changes, the force itself, than to the mass changes. Okay, very good. So what do you say then? It would decrease how many times?
9 times.
9 times, very good. Number 5.
Let's see. 3 times smaller. Then the gravitational force would be made 9 times stronger.
Yes, very good. Excellent. And next one.
What would affect the strength of gravity between the Earth and the Moon while making the moon? Oh, wouldn't it be the distance?
Yes. Yes, very good. Very good. Great. Okay, second part. Okay, so do you feel better now about that first part?
Yes, I do.
Okay, good.
Okay. And the picture below the Earth. In the spacecraft the strongest on the spacecraft. At which lettered position of the gravitational perspective? Where's the spacecraft? Show next. Okay. So the gravitational pull would be greatest at position A for the spacecraft because it's in very close proximity to the Earth.
Which one?
At position A.
Very good, because now what's the reasoning that you're using, that the gravitational force between the Earth and the spacecraft will depend on the mass of the Earth and the mass of the spacecraft? Well, you cannot change that. That's given. But what you can change is the distance. The closer you get that spaceship to the Earth, the more force it will feel. Very good. So A is the correct answer. Okay, very good. How about the next one?
Which one? Strongest. So that would be H, correct?
Exactly the same reasoning, right?
Yes.
Okay, very good. What's the next one?
Oh, number 9. Let's see. Oops. Let's see. Spacecraft is halfway at point D. How does this string from direction? Net force. So if it's at point D,
Yeah.
means that the Earth exerts a greater gravitational force because it has greater mass.
So let's assume that point D is like a midpoint, even though maybe like E looks more like the midpoint. So in the midpoint, what's the same?
The distance.
So then that's not a factor. So then which one will pull more will simply depend how their masses are comparing. And you're correct, then the Earth would pull more, right? Because it has like more mass. How many times more would the Earth pull?
I don't know.
I think it says over here the Earth's mass is about 80 times that of the Moon.
So it would pull 80 times more.
Exactly. And so that's like, by a lot more, right, than what the Moon would pull in the middle. Okay, very good. What's the next one? Oh, actually, in this number 9, it tells you kind of to make a sketch, right, and show the direction of the net force. And so I can do that, like, we can talk and then I can do that. So for example, if this is like, whatever here, that's the midpoint, let's say, that we are exploring. So you just told me, right, the Earth will pull like, 80 times more. So let's say this is the pull of the Earth. The Earth pulls the probe towards itself, and the Moon basically pulls like with something like this, 80 times less, right?
Yes.
And so the net force is what now? So for the net force to define, you have multiple forces acting. And so the net force would be simply the difference between these two forces. This will be important for one of those homework files. I think it's the number 5 that asks you to find the net force, yes? So the net force, you have to find both forces, and then you find the difference. And so you can see that this is the greater force. So the net force will be basically in the direction of the Earth's pull, so almost like identical like the Earth's pull. Agree? Yeah. So basically just like this minus this little tiny pull towards the Moon. So this is the net force.
So how do we determine the exact values?
You don't have to calculate ever, like, you know, the exact values. This is all just like conceptual. So it's just like for you to understand, and you can understand this, like, you know, you can think about yourself, for example, and then you stretch your arms out and you have, like, you know, somebody pull on one arm and somebody else pulls on the other arm. What can happen to you? Assuming that they pull, like, you know, gently enough, they're not going to tear you apart. Okay. So what can happen to you? Like many things, right? If one pulls more, you are going to move in that direction. So that means, like, you know, the net force will be in that direction. But if they pull with the same forces, but in opposite directions, nothing will happen to you, right? You're going to remain like standing and you're not going to move. So that's basically why net force is important, because it tells you if there is that net force, the object will change motion in that direction.
Right.
Make sense?
Yes.
Okay, good. Okay, next one.
Let's see. Pretend, imagine. Okay, so.
So once again, remember now with these arms that I gave you the example, if people are pulling with the same forces but in opposite directions, nothing happens to you. You remain stationary. That's the same idea in the question number 10. You want to fix your spacecraft, so you want to find that like sweet spot where, like, you know, forces will cancel out, the force from the Earth and the force from the Moon, where the net force is equal to 0. So where would that spot be? What do you think?
It would probably be closer to the Moon.
Much closer to the Moon, right?
Yeah.
Because even in the midpoint, the Earth pulls like 80 times more, right? Yeah. So if you look at this equation, that's that extra thing that I asked you, right? The Earth pulls like 80 times more. And so if you want to cancel that 80, you know, you have to get like 80 downstairs. And that means, like, you know, what number do you square to get 80?
Let's see.
I mean, approximately. So what number squared will give you like 80?
8.
It's going to be 9, right? 9 times 9 is like 81. So it's going to be number 9, which tells you if you want to find that spot where the forces will add to 0, then you have to be kind of 5 times as far from the Earth than from Mars, right? So you have to compensate by that from Moon, sorry, with that greater distance to basically get the same forces. So probably the spot H would be the one that is correct, right? Does that make sense? So you have to be really, really close to the Moon. Okay, very good. So that's the bonus calculation that we were talking. Okay, number 3.
So if it has a greater radius, doesn't it mean that you'd be heavier? No, you'd be lighter, because I don't know
either. So now your weight, what is the weight? The weight is simply gravitational force that Earth exerts on you or me, okay? So going back over here, it's the same force, okay? But just now you don't have the Earth and the Moon, but you have what? The Earth, and then you have like yourself, yes?
Yes.
Okay, so they tell you that the size of the Earth remains the same. This is now the distance from the center of the Earth, so radius of the Earth. So let's say that stays the same, but what happens over here? The mass of the Earth doubles. So somehow, again, hypothetically speaking, the Earth has more mass. It's like much denser. What happens to the force between the Earth and you, or to your weight, basically?
It increases.
It's going to increase. It will increase. How many times?
Oh, how many times did it say? Let's see. 5. Twice as much.
Twice, very good. So if you have like 100 pounds now, you would have like 200 pounds then, right? That would be your weight. Okay, good, perfect. See, it's not that hard, I think.
Yeah.
Okay, good. This is much easier in the class, right? Because but online, you know, it's good that we have Zoom meetings, so then we can record and the other students will get help as well. So what do we say over here? If the planet has the same mass as Earth, but twice the Earth's radius, how much would you weigh?
So if it had twice the Earth's radius, would that mean that you're twice as far from the center of the Earth?
Yes, yes, awesome. And that would mean what?
That you would be twice as light as you were. You'd be 2 times lighter than you were before.
Are you sure that it's 2 times?
Oh, no.
You would be lighter, so you're good, right? The intuition is good. You're further out from the center, you're gonna be lighter. But how many times?
It wouldn't be 2.
Look at the formula.
Let's see. So that would be the denominator, correct?
Downstairs.
Oh, so you're increasing the distance. Oh, it would be 4 times.
Yes, very good, right? So always be careful. It's more sensitive to the distance changes. So if you make Earth twice as large, your weight would be like 4 times as low.
That makes sense.
And that's like, you know, a problem when you think about people want to go to Mars, right? But Mars is much like, you know, lower mass than the Earth, so less gravity. So that would affect like, you know, our muscles. But also like many planets that we find now outside of the solar system, they're bigger than the Earth. And that would mean like also, you know, more massive. So that would mean like, you know, more gravity, more weight you would feel if you go there. And that wouldn't be good for us as well, right? It would make like our heart like pump harder and all of that. So, you know, we are built exactly for the conditions on the Earth, and there is like a really small like comfort zone where you can go, right? So for your body to function properly.
Oh my gosh, that's crazy.
I know. Okay, what do you say about number 13?
13. The planet has the same mass, but half the radius. How much you do weigh? What does it mean by half the Earth's radius?
Yeah, so again, somehow magically, okay, you keep the same mass of the Earth, but you now squeeze it, right? So it doesn't have its own radius, but it has like half of its radius.
Okay.
Now what happens? Are you closer to the center of the Earth?
That means you're closer to the center of the Earth.
So your weight will do what?
Or 4 times as heavy.
Yes, very good. 4 times as heavy. Now I'm asking you all of you this question so that you can think now, you know, the black holes, for example, they're going to be like, you know, you take the star and you shrink it more and more and more and more. And basically, but you keep the same mass. And so you can immediately now like build that understanding and intuition how gravity works. Because you're doing that, you're shrinking the radius, then the gravity increases, right? And for the black holes, for example, it's going to increase to such like values that even the light will not be able to leave the black hole, right? And that's why they're black. So that's why, like, you know, this is like a good worksheet, maybe a little bit challenging, but like gives you this understanding to understand, like, you know, what's coming up in the course.
Yeah.
Okay. Okay, how about this one? That's a hard one.
The moon has mass is also 4 times smaller, steady on its surface. We are about 4 times closer to the surface. Or less or the same. Okay. It's gonna be good. The moon has.
So let's think together. Moon has 80 times less mass than the Earth, right? So if it was then the Earth size, you would feel what? Your weight would be what?
If the moon was the Earth's size.
But it has like 80 times less mass, then what would happen to your weight?
80 times less mass, which would mean that you'd be heavier.
Less mass.
Less mass?
Mm-hmm.
You'd be lighter.
You would be lighter. How many times?
By 80 times.
Very good. But then Okay, so by 80 times you would be lighter because of the mass, that it has less mass, but also says it's 4 times smaller. Moon is 4 times smaller. Now, what does that mean? You are 4 times closer to the center of the moon. Will that increase the weight or decrease the weight?
So if you're closer to the center of the Earth, it means that you'd weigh more.
Yes, how many times more?
So 16 times more?
16 times more, very good. And so would you now, so you calculated because of the moon's mass, you would weigh 80 times less, but because it's smaller and you're closer, you would weigh 16 times more. And so if you do that, divide your weight by 80 and then multiply by 16, what do you get?
You divide your own weight?
Mm-hmm. So this is what we said. I'm going to write whatever is your weight. Okay, let's call it double W, right? You are going to be 80 times lighter on the moon. This is number 80 because moon has 80 times less mass. But also moon is smaller, 4 times smaller in radius. So that means you are 16 times, you will have 16 times more weight because of that, yes? So when you do this like algebra now, like analyze this like whatever, like fractions over here, what do you get? You can like simplify 16 and 80, what do you get? Roughly, again, roughly.
2 over 5, correct? Is that not right?
2 over 10, okay? So if you divide this by 8, you get 2 and then 10 here, and then you can do another 2, right? Divide by another 2, so 1 upstairs and 5 downstairs. So you would get basically that your weight would be 5 times smaller on moon, right, than it is on Earth.
Okay.
Because of that combination. Moon is smaller, you're closer to the center, but it's also less massive. So, and this is approximately true, right? Mm-hmm. There is 5 times less gravity for you if you go to the moon. And that means like, you jump, you push the same way like you would push on the Earth. And I don't know on the Earth how far you jump, like 2 feet maybe. On the moon, you would jump 10 feet in the air, right?
Yes.
And if you weigh 100 pounds there, you would be like 20 pounds. Like a 6-month-old. Okay, does that make sense?
Yes, that makes sense.
Okay, very good. Okay, number 15. This is all correct. Okay, this is all like, what's coming up. So at the end of its life, the sun will become a white dwarf.
Our sun?
Yes, our sun. So at this point, the radius will reduce by 100 times. And I don't know if you remember it, but the sun is 100 times bigger than the Earth right now. So that means the sun will end its life being basically the size of the Earth. So what will happen to the gravity exerted by the sun on Earth?
So if it's reducing by 100 times?
Its own size, right? But the mass remains the same.
Will the gravity remain the same?
Yes.
The same. No, the same mass.
Exactly. Very good, right? The gravity between the Earth and the sun only depends on their masses and their distance. And none of this is changing, even when the sun becomes a white dwarf, okay? So even when the sun is done producing all of this energy, that we get, we are still going to go around the sun, right? Because the gravity will not change, okay? So that's good to know.
But then the life on Earth would obviously die because...
I think we don't have, like, that's like 5 billion years down the road when this will happen. I think we will destroy ourselves much sooner, right? Oh. It's not going to be a cosmic reason, I think.
Okay.
I know. Okay, number 16, what do you say?
Okay, at the end of its life, the sun will... Its mass will remain the same. What will happen to the force of gravity on the surface? The force of gravity on the surface of the sun, as it is affected by the Earth?
No. So basically you can think now if you were standing on the sun, right, you would feel some force of gravity because of the size of the sun and the mass of the sun. Now what would happen if you keep that same mass but you shrink sun 100 times? So it becomes like 100 times smaller. You get 100 times closer to the center of the sun. What would happen to the force of gravity at the surface?
It would be 100 times greater. because
It would be greater, but not 100 times, but
would it be squared?
don't forget that square, right? So 100 square, and that is 10,000, yes?
10,000 times greater. Okay.
Yes, can you imagine that? That's really true, okay?
Wow.
So when the sun becomes white dwarf, it will be 10,000 times like more gravity on the surface of the sun. So the light will not actually anymore like leave in straight paths away from the sun, but it's going to curve a little bit as it leaves the sun. It's going to be affected by that, like, much greater gravity.
Oh, wow.
I know, so many fun things in astronomy. Okay, let's see now. I wanted to clear now this. Okay, so what do you say? I think this is from Homburg. This one is from Homburg, right? I think this is number 6 or something. It's exactly the same table. You want to do this because this is asking you how to calculate the force of gravity between star 1, star 2, and then given the distance between these two stars.
Yes, that would be helpful.
Okay, so what do you say? So it's the same formula that we were talking here, except that, like, in all of these calculations, you can ignore this G, okay? So basically what we are talking about is just like force of gravity is proportional to one mass times the other mass divided by distance squared, okay? Because that G is a small number and just like makes everything, I don't know, calculation hard.
Mm-hmm.
Okay, so once again, what did I just tell you? This is what you're applying here. The force is going to be proportional. This means like proportional to M1 and then M2 and then over distance squared, right? And so you're given now in the table everything that you need to do this calculation.
Okay.
So let's see, this pair A, what would be the force?
So the force would be, okay, so you do 4 times 2, which is 8,
divided by
2.
By 2?
Which is
No, wait, you are constantly forgetting that one little thing. 2 squared, okay, very good. So what do you get?
2 squared is 4. That would be 8 divided by 4, which is 2.
Yes, very good.
Okay.
So good. So the force here would be 2. Very good. How about the second case?
So that would be 2 times 8, which is 16. 16 divided by 2 squared, which is 4. And then 16 divided by 4 is 2. No, it's 4.
4. Okay, good. Okay, so that's it basically. So you have handle of that. So you'll get then the numbers here, and then you just compare those numbers, right? Which one is greatest and which one is least.
Okay, that makes a lot of sense.
So don't forget to square the distance, okay?
Yeah.
Okay, good. Would you like anything else to go over?
I don't think so. I think I got it.
Okay. I mean, I know, like, usually I can show you something else that it's, let's see. I can still actually share the screen. Let me just see how to go to here. Okay, so if I go back. So not the worksheet, but the homework. Did you take a look at the homework?
I have not.
Oh, you have not. Okay. So I think this is gravity number 6 is that table. Okay. So you're all set with this one. Okay. That was that one. But let's see if number 4. Number 3 is the same like number 4. But so here is the number 4.
Okay.
So you have some asteroids over here, these potatoes over here, those are like the asteroids, like irregularly shaped. And it's asking you, so okay, they have some masses and they have some separations. So you have to answer over here the strength of the gravitational force exerted on the asteroid on the left side. So this asteroid over here on the left side, where does it feel the greatest force? You don't have to do any calculations. Even just like when you look, you can say, right?
Oh, okay. Oh, so it would feel the greatest force, I think, at the last image at the bottom.
In the pair D. And why would that be the case?
Because the asteroid on the right is largest.
Yes.
The greatest mass.
Yes, very good. And so once again, don't confuse yourself and say, let's now just look at the pair D, right? In this pair D, both of these asteroids, the big one and the little one, they feel exactly the same force, right? And that force simply depends on the mass of the little one, of the big one, and then how far apart they are. So they both feel the same force. But this force in this pair is greater than the force in the pair C. And the reason is that simply there is more mass in this pair, right? As you can see, A, B, C, D, all of these pairs are at the same distance. But in this pair, we have the greatest amount of mass. So that would mean then the force will be greatest in this pair.
Okay.
Okay. Uh-huh.
Got it.
Good. And then it's asking you something else over here. So using Newton's second law, and that's the one that tells you basically how the objects respond to the force, right? Mm-hmm. The more mass they have, the less they will respond to the force, right? The less they will be accelerated. So rank the acceleration that the asteroids located on the left side of each pair would experience. So again, you're looking at these 4 asteroids on the left side of these pairs. Which one? And how much acceleration?
Okay. So I think that in image D, the small asteroid would have the most acceleration.
Because? Because
of the asteroid on the right has the greatest mass.
Because there is more force in this pair, right? Okay. There is more force. You're applying more force on this asteroid than to any other of these asteroids, and they're all identical, okay? So that is also a helpful thing over here, that they all have the same mass, right? And so analogy from everyday life, you can take like 4 cans if you want, they have the same mass, and you push one harder and the other one less. The one that you push harder will, like, you know, accelerate more, right? So that's like exactly what's happening here with these like asteroids. Okay, so that one, perfect. And then let's see one more. I'll ask you just like one more, and then we don't have to do any more. I think number 5. This one is hard. Okay, because again, it's asking you about the net force, okay? So take some time, read if you want, and then we can talk about that.
Let me open it on my screen. Awesome. Let's see.
Okay, so do you understand what they're asking?
Which diagram would have the most
net force, right? Exerted on the center asteroid by its 2 neighboring asteroids. So it's asking you, this asteroid is in the middle, right? Which one feels the greatest net force? And just to help you a little bit, like, you know, if you're here and thinking about this like center asteroid, what is happening to this asteroid? What does it feel?
So, which asteroid?
This one, let's say A, right? The first one in the middle. So what does this asteroid feel?
So it's, if we're looking at just the distances.
No, don't even look at the numbers, just tell me. So there is like an asteroid in the middle, then there is one to the left and one to the right. So what's happening with this asteroid in the middle? What does it feel?
It feels a gravitational force from the left and to the right of it, but more force from the left side.
Very good, excellent. So it would feel like something like this. Yes, this is the little asteroid pulling it towards itself, and then it would feel this one, yes, pulling it that way, okay? So you have these two pulls. Obviously, there is more pull towards the left, as you said. So the net force, remember, once again, is the difference between them, okay? So the net force would be something like this, yes, in this direction. And so how do you find this now, net force? Now you have to do the math, okay? But you know how to do it because you did it in that table. So to find this net force, you have to find this force, which would be basically what?
So that would be 5 times 10, 15 divided by, oh no, 5 times 10, 50 divided by 9.
Very good. So you get that number, and then you get this number, yes, which is going to be what? This other force.
30 divided by 9.
Very good. And then you find the difference between them, right? And that's your net force. Does that make sense?
Yes.
Very good. Okay. And then so you do that for all of them and then see which one has the greatest net force.
Okay.
Perfect. Perfect.
Okay.
I think that you're all set. The rest of the homework is not hard.
Yeah, I would have been really confused about this.
I know. Well, you know, this is my 40th time, I think, teaching this. So I know all the confusion points that students have, which is helpful, I think.
Okay.
Okay, great. So I'll see you then next week. Is this week easier than the previous one?
Very much so, I think.
I think so. I think so. So as I said, like, you know, it's going to get like, I think easier, more straightforward, more like, you know, common sense. So just relax and keep on like working.
Yeah, because I think we've all taken physics in high school and we deal with gravity every day.
Okay. Maybe. Okay, good. Well, nice seeing you, and then I'll see you next time.
Yes, thank you so much.
Thank you. Good. Good night.
Good night.